Modern computing is defined by a landscape of rigid logic, a world where every function is locked into a fixed sequence of binary code. We usually contrast this with the ancient world, viewing it as a time driven by the fluid, unstructured beauty of art and oral tradition. But the binary patterns we use to power our devices today began thousands of years ago, tucked inside the cadence of the spoken word. In the ancient Sanskrit tradition, the line between the mathematician and the poet was essentially non-existent. Around the 3rd century BCE, a scholar named Pingala began his work within this intersection of art and logic. We know very little about his personal life. No record of his birth date, his childhood, or his family has survived the 2 millennia since he lived. Historians place him within a highly respected community of scholars, where the study of sacred Sanskrit texts was the primary focus of life. He was raised in an environment where all forms of knowledge were considered sacred and interconnected, providing the specific intellectual tools needed to see mathematics where others heard only music. This work began in the rigorous educational centers of ancient India, in the quiet courtyards where students gathered around their teachers. Through the guru-shishya tradition, knowledge was transmitted orally. Without a reliance on written books, every lesson had to be committed perfectly to memory. Pingala and his peers memorized staggering amounts of information, entire systems of grammar, complex philosophical debates, and thousands of epic poetic verses. This level of memorization functioned like a high-speed data retrieval system, where Sanskrit grammar served as a complex, functional linguistic operating system. The need to store this data accurately within the human mind required the language to follow strict, predictable rules, creating a natural pathway toward mathematical discovery. Sanskrit poetry was built on a predictable, scientific framework. Every line was governed by precise vocal syllables, alternating between short and long sounds. These clusters created a structural rhythm. Looking past the words, Pingala focused entirely on the arrangement of syllables themselves. He began to wonder if these repeating patterns could be mathematically mapped, counted, and organized. By isolating the rhythm into just 2 variables, short and long, Pingala had identified the same dual-state logic used in a modern binary system. By deconstructing the layers of a poem, he exposed the mathematical framework that had been hiding within the language all along. This work resulted in the Chanda Shastra, a comprehensive text where Pingala systematically cataloged every possible poetic meter. To knock these phonetic variations, he developed early forms of combinatorics, showing how a few simple rules could create an endless array of patterns. His system could calculate and predict every mathematical possibility within the 2-syllable structure. In his effort to categorize literature, Pingala had detailed the foundational logic that would later be used to drive computational thinking. Pingala made these discoveries in an era without electricity, calculators, or machines. His breakthrough came from an education where logic, grammar, and rhythm were studied as a single integrated science. By decoding this simple rhythm of the human voice, Pingala uncovered the binary structures that continue to organize our world today.